Welcome again to the subject of eco-cities. In the previous modules, you have seen that urbanization is a pervasive phenomenon in today's world, and you have seen Professor Martin de Jong explain the differences between different urban development concepts. He also showed that most eco-cities and low-carbon cities in China do not live up to their environmental promises. This makes it all the more relevant to investigate if urbanization as such is good or bad news for the environment, and to investigate what role infrastructures can play in building eco-cities and in eco-transformation of existing cities. Let me briefly go back to the essence of a city. Its physical expression is in the built environment, homes, offices, industrial facilities and infrastructures. But a city is not only defined by its physical dimension, it is also defined by its socio-economic dimension, including, for example, labor market, jurisdictions, commuting patterns, and by its cultural dimension, which gives it a distinct identity. The city is a socio-technical system, and given the many non-linearities in the interactions between citizens, authorities, industries, and other actors, within and with the built environment, it is also a complex adaptive system. Previously, I showed you how the Pearl River Delta changed over the past decades. The NASA satellite images do not leave room for any doubt that the natural environment was drastically changed as a result. Nature made way for buildings and pavements. Habitats have shrunk and been lost. Rural agriculture has been replaced by manufacturing industries. Surface waters have been polluted and air quality has been affected by particulate and gaseous emissions from industry, power plants and car traffic. Cities worldwide account for nearly 70% of global CO2 emissions. They demand huge amounts of resources and produce huge amounts of waste. Does all this imply that urbanization is bad news for the environment by definition? The short answer is, it is often so, but it is not inevitably so. Urbanization can be good news for the environment, as cities can achieve higher levels of resource efficiency than can be accomplished in a sparsely populated rural area. I already explained that cities do more with less in comparison with rural areas. And the bigger cities get, the more productive and efficient they tend to become, as found by Louis Bettencourt and Jeffrey West. When the size of a city doubles, its material infrastructure, think of the total length of roads, pipelines, cables, does not. Instead, these quantities rise more slowly than population size. A city of 8 million typically needs 15% less of the same infrastructure than do two cities of 4 million each. In terms of physical infrastructure needs, cities show a sublinear scaling pattern. The bigger the city, the more efficient its use of infrastructure, leading to important savings in materials, energy, and emissions. Besides Louis Bettencourt and Jeffrey West at the Santa Fe Institute, many other research groups in the world are working on a better understanding of cities as complex systems and on visualizing the emerging structures and dynamics of cities. Let me just briefly refer you to the work of Michael Beatty and his co-workers at the Bartlett Center for Advanced Spatial Analysis at University College London, or to the work of Yuval Portugali at Tel Aviv University. Density is, of course, a factor that influences how efficient a city can be. This can be illustrated from a comparison between cities worldwide of per capita energy consumption for transport. As shown in this graph, the densely populated megacities in Asia are far more efficient than the relatively thinly populated American cities. In the list of 26 megacities that I showed you previously, New York City is the one with the lowest population density, whereas it is relatively densely populated in comparison with other cities in the US. In a denser, more compact city, people consume less energy resources for transportation, as walking, cycling, and public transport are viable alternatives to commute for many of them. But in a less densely populated city, there is no viable business case for public transport, so people keep commuting in private cars, thus using more energy, emitting car exhaust fumes, and clogging the city's road system. According to Mark Roseland and Fiona Harvey, eco-cities should be built according to the following principles. They should have a well-planned city layout and public transportation system that makes the priority methods of transportation as follows possible: walking first, then cycling, and then public transportation. They should operate on a self-contained economy, with resources needed being found locally. They should be completely carbon neutral and use renewable energy production. They should apply resource conservation principles, maximizing efficiency of water and energy resources, constructing a waste management system that can recycle waste and reuse it, thus creating a zero waste system. They should restore environmentally damaged urban areas and ensure decent and affordable housing for all socioeconomic and ethnic groups, and improve job opportunities for disadvantaged groups, such as women, minorities, and the disabled. They should support local agriculture and produce. And they should promote voluntary simplicity in lifestyle choices, decreasing material consumption, and increasing awareness of environmental and sustainability issues. But as we can see at a glance, many of these criteria are not easily applicable to megacities. It is hard to imagine a megacity which is completely self-sufficient in food, water, and energy. In rural areas where people live in a relatively isolated fashion, it may be possible to be self-sufficient. However, the rural model of living off-grid, with solar panels on your roof, cutting your own trees for firewood, pumping water from your own well, disposing of your wastewater in your own septic tank, and burning your own waste, or just leaving it in your backyard, that is not feasible in cities. It does not take much imagination to see what would happen if all city dwellers would do the same thing. The city would simply become unlivable. Only the solar panels in this example would be applicable in the city, but you will also understand that the roof surface area available in a dense city with many high-rise buildings would probably not be enough to provide electricity to all the people living underneath these roofs. Renewable energy needs space, and space is a scarce and therefore expensive commodity in cities. Densely populated megacities need to harvest their renewable energy resources outside the city, implying that wind parks, photovoltaic parks, concentrated solar power plants, and hydropower plants located at favorable locations, often far from the city, must supply the city through the transmission grid. Considering the current state of the art in renewable energy technologies, it is hard to imagine a megacity that would be entirely self-sufficient in renewable energy. But let's hope that the future brings so. The good news for now is that the provision of water and energy to urban residents and the removal of waste and wastewater can be accomplished with higher efficiency and with better quality of service than in rural areas, as infrastructures can do the trick, building on economies of scale and scope. Let me give you an example. AEB, the Amsterdam Waste and Energy Company, owned by the Amsterdam municipal authorities, annually processes 1.4 million tons of municipal and commercial waste. In its waste-to-energy plant, the waste is incinerated, producing 900 kilowatt-hours of electricity and 91 kilowatt-hours of heat for district heating per ton of waste processed. By separation processes before and after combustion, ferrous and non-ferrous metals are separated and recycled. Per ton of waste, AEB produces 16 kilograms of iron, 3 kilograms of other metals, such as copper and aluminum, 4.5 kilos of gypsum, which is mainly separated from the flue gas, and 209 kilograms of construction materials as an alternative for gravel and sand. The company also supplies steam to industries in its vicinity within a 5 kilometers radius, and it supplies lower temperature heat to 20,000 homes connected to its district heating network. And the ambition is to expand the district heating network to 230,000 homes in 2040. The Amsterdam water utility, Waternet, which produces drinking water for the city of Amsterdam and treats its wastewater, this company supplies the biogas produced from its wastewater treatment plant to AEB for conversion into electricity and heat. And at present, due to improved efficiency in wastewater processing and in the collection of organic wastes, the amount of biogas produced has increased to the extent that Amsterdam is becoming a green gas producer. The biogas is upgraded to the Dutch natural gas quality standard and sold as green gas in the market. The distribution of heat as steam or as hot water is not economical over large distances. Therefore, the denser the city, the more economically waste heat can be put to use for residential heating. Whereas the Netherlands is just starting on the path of using heat, often waste heat, from cogeneration units, thermal power plants, waste incineration plants, and other industrial sources for district heating, Denmark is a country with a long-standing tradition of district heating. And Denmark is now using its district heating systems to store energy during days of surplus wind power. For this purpose, they use large immersion heaters to convert electricity to heat, which allows the cogeneration plants to be shut down temporarily. And that reduces fossil fuel use and reduces the overall carbon intensity of the Danish electricity system. In the surroundings of the city of Leeuwarden in the Netherlands, which is situated in an area dominated by dairy farms, biogas is harvested abundantly. The biogas is used to fuel cogeneration plants that supply electricity to the local distribution grid and heat to residential districts. The province of Leeuwarden, the province of Friesland, is the first in the Netherlands where a biogas infrastructure is now being developed, which enables a multitude of farms which produce biogas from manure fermentation to feed their biogas into the pipeline system and transport it to a central plant where the biogas is upgraded to green gas. And that green gas is either fed into the natural gas distribution grid, but it is also used as a car fuel. The Danish city of Zonderborg, with approximately 76,000 inhabitants, is one of the cities in Europe that made an explicit decision to shift to a zero-carbon green economy. Zonderborg's objective is to become carbon neutral by 2029. To this end, the municipality and district heating suppliers established a partnership with citizen participation. Among the actions that are already underway are replacement of natural gas in district heating with renewable energy sources such as geothermal, solar, and biomass. A new pipeline that will connect all existing district heating networks in Zonderborg. Generating biogas from pig manure, from organic waste, and from energy crops. And they will generate power from biogas, wind, and photovoltaic, and install photovoltaic cells and heat pumps in the rural parts of Zonderborg. However, in the words of Andres Piebalgs, former European Commissioner for Energy, the cheapest, most competitive, cleanest, and most secure form of energy for the European Union and for any place in the world remains saved energy. Especially in the built environment, there is tremendous potential for energy saving by designing homes for better use of natural light, natural ventilation rather than air conditioning systems, and for better heat or cold retention. And especially the latter, heat or cold retention, is a matter of building quality and standards such as LEED and BREEAM, which are already in place to ensure energy saving, both at the level of individual buildings and at the level of neighborhoods, districts and cities. In the existing building stock, much can be improved with thermal insulation, more efficient heating and cooling systems, and low energy glazing.